So this is May, June 2022, paper 42. P42. So define gravitational potential. We are familiar with this already. Work done per unit mass to bring it from infinity to that specific point. And of course, I've said that before. You can consult the book and the marking scheme to memorize the definitions. These are one of the repeated definitions. You can do that. He says, starting from the equation of gravitational potential due to a point mass, show that gravitational potential energy is this. So if you have to start from gravitational potential, that is negative gm over r, and show that the potential energy is this. So that is simply put forward, electric potential energy is actually, or gravitational potential energy is actually equal to phi multiplied by the mass that you're moving in that gravity, or in the presence of that gravity. So simply put forward, that would have been negative gm over r multiplied by m, would have been gmm over r. The negative suggests that this is work done by an attractive force, or the system does this work on its own. You didn't do this. The gravity is going to attract this object on its own. The work done is negative. Or another scientific way of saying this is that work done by an attractive force is negative. Okay, so masses are given, speeds are given. You can pause the video, read the question, or if you have it in printed format with you, you can read the question on your own. Okay, I'm going to just skip to the parts which are going to matter in solving the question. So he says that at x, the comet is this much away. So it is at a distance of 8.44 power 11. So 8.44 power 11, it's away from the meteorite or this comet at x. And when it comes to point y, it is this much away. So 6.38. So this distance would have been 6.38 into 10 raised to the power 10 meters. Okay. All right. Of course, up to y, I've exaggerated so that we can at least look at it. Otherwise, that would be very tiny space. The arrow would not have been visible to you guys. Okay. So since it is approaching, I can say that the velocity may increase, or it will increase because it's falling onto the star. Okay. And the common example of this is if you throw an object from the building, its speed increases. So in terms of the Earth's gravity or the star's gravity, at least if the comet is moving towards it, it is losing gravitational potential energy, and that is converting into speed. This is preemptive idea. Let's move on to the question. He says, calculate the comet star, consider point masses. Okay, this actually only enables us to use the equations that we've learned in this chapter. Calculate the magnitude of change in gravitational potential energy of the comet from position x to y. So first he asks you to calculate this, so that do you understand this idea or not? And then he's going to ask you to apply this. So there are two ways to do this. Since you're trying to find the change in gravitational potential energy, you could have found the change in potential or the change in potential energy and then multiply it with mass, right? The mass that you're moving in its vicinity. Or you can just directly do with the equation, okay? Because if you put this equation as gmm over r, then you have to actually take the difference of two different locations. Because first the gravitational potential has to be found at x, then at y, and then you have to take the difference of that. That what is the gravitational potential to reach this point, and what is the gravitational potential to reach this point. Then the difference between the gravitational potentials, and then you find out the energy of the gravitational potential. Now notice that this is the longer method. This is the process that we have to do because the value of g is not constant. Previously, when g was constant, we simply used mgh in O levels and IGCSE, and at least A level first year. We used to use this formula for mgh, for the potential energy, but now we can't do that because the value of g is equal to gm over r square. It's changing at all times. It is different at this point. It is different at this point. It is different at this point, so on and so forth. So many levels, it is going to be different. So that's why we have to take care about this idea that value of g is changing at all times. That is why we have to employ this method. So what does it come down to? So this comes down to this idea. Let's take gmm at least on the outside as a common to make the calculation easy. So 6.67 into 10 to the power minus 11 into the larger mass, which is given to us as 1.99 into 10 to the power 30. The smaller mass is 2.2 or comet is 2.2 power 14 kg, and then multiply this with 1 over r, which is the furthest distance or the closest distance, 6.38 into 10 raised to power 10 minus 1 over 8.44 into 10 raised to power 11. You see, this will be final minus initial sort of thing. Final minus initial, but since both of them have a negative sign, this negative becomes positive. So this comes over here and this one comes over here. As simple as that, okay? All right. So when you're done solving this comes out as 4.23 into 10 raised to power 23 joules. So this will be 4.23 into 10 raised to power 23 joules. State with reason whether the energy change potential is an increase or decrease. So this is actually a decrease. The gravitational potential energy decreases. And the reason, simply put, is that the work done is being done by an attractive force. If an attractive force does some work, then the work done is negative. Primarily, what's actually happening is that the gravitational field is attractive at all times. And if you allow an object to fall because of that gravitational field, the gravitational field is in the same direction, the attractive force is in the same direction. So when the field direction and the force are exactly the same and the object moves this distance, so that F into D is going to become negative. In physics, if an attractive force does this work, this is negative, which means that you didn't do this. The system has done this on its own. So whatever the energy was invested in the system when this was carried upwards has now been demanded back. Okay. User answer in B1 to determine the speed in kilometer per second of comet Y at point Y. Exactly the same logic as we did in O levels. An object thrown from a certain height reaches Earth, what will be its velocity? So we understand that the change in gravitational potential energy should be equal to half mv square, or at least the change in kinetic energy. So this is where you're going to get it wrong. So this is equal to change in kinetic energy. Why? Because previously it already has a speed of 34.1. It already possesses some kinetic energy. So whatever we have invested in terms of gravitational potential will show up in terms of an increase in kinetic energy. So the change in gravitational potential has been found in the previous part as 4.23 into 10 raised to power 23. The change in kinetic energy will be half m, which is 2.2 into 10 raised to power 14. But here is the tricky part. You see, since you're finding the change, it would have been half mv square minus half mu square. Final kinetic energy minus initial kinetic energy. But since half m is common for both of them, we're writing this down as v square minus 34,100 meters per second square. And of course, the velocity has to be converted into meters per second before using this formula. Okay. Please don't forget that these are actually squares independently. Please notice that a square minus b square is not equal to a minus b whole square. Don't do it like this, that you take this whole square outside and then subtract it. This will be wrong. Please use some mathematics. When you're done with this algebra, for example, take this 2 over there, divide it with this number, and then take this over to the other side and add it into this equation, and then take the under root because v is a square. So v comes out to be equal to 70,800 meters per second, which is going to become 70.8 kilometers per second. By dividing it with 1000, we convert meter into kilometers. A second comet passes point X. Where is point X? Point X is over here. Let me clear out this diagram. So yes, point X is over here. Okay, another comet passes this position. Fine. And then he says that it's gradually losing mass. Okay, the mass of the comet passes through the X is same as of comet B. So just with reason how the path will not be affected. Why? Because what logic are we using? We are using the logic of change in gravitation into change in kinetic. So this would have been gmm over r equals to half mv square. Now, mass of the comet cancels out from both sides. It does not matter. The main planet is responsible for controlling all of this behavior, not the comet itself, right? In the gravitational area, or the gravitational field along which you are moving, along which you are actually traveling, that will matter. Okay, so, and the other thing, why the path will not matter, because the velocity is not changing, because the mass is irrelevant. So the centripetal acceleration leading to v square over r will not change. So the centripetal force leading to mv square over r will not change. The force is not changing, the acceleration is not changing, the velocity is not changing, so nothing is changing. So same path. Why we reach this conclusion? Because mass has no effect or has no participation in the system. Same thing happened in O levels as well, or IGCSE as well. You throw the mass and you equate half mv square equals to mgh. M cancels out and you're left with 1 over 2 v square equals to gh. It does not matter what you've thrown from a height. It only matters when the air resistance is present. Okay, all right. So state Coulomb's law, again, a very common definition. We know that Coulomb's law is actually equal to Q1, Q2, product of charges divided by the square of separation, exactly like the gravitational. And this is proportional, of course. This is being divided by 4 pi epsilon naught as a constant. So look up the Coulomb's law from the book, memorize it. So it's the force being proportional to the product of charges, Q1 multiplied by Q2, but force being inversely proportional to the square of separation. We have just described the formula in English. That's what we've done. Simple. Positronium is a system in which electron and positron are orbit, okay, with the same period around the common center of mass, okay, fine. The radius of the orbit is this given. Explain how the electric force between the electron and positron causes the path. Okay, again, he's asking the justification for circular motion. So there is an electric force, or you can say the electric force is perpendicular. So, sorry, not electric force, but centripetal acceleration. So there is an acceleration, right, being perpendicular to velocity. And where this acceleration comes from? It comes from the electric force providing the necessary centripetal force, producing the acceleration which is perpendicular to the velocity. Hence, it enters a circular motion or circular orbit. This has been one of the repeated questions. Why is it moving in a circle? With the requirement to move in a circle is an acceleration and a velocity perpendicular to each other. And acceleration comes from a force, of course, centripetal force. But what is the cause of that centripetal force? Who gave it to them? The electric force between the positive and negative charge. Electron is negative and positron is actually a positive charge, as we've done from the PET scan and PET scan. Show that the magnitude electric force, okay, fine, very easy. So electric force is equal to Q1 multiplied by Q2 divided by 4 pi epsilon naught r square. Now we know that the charge on the electron is 1.6 into 10 raised to the power minus 19. We know that the charge on the positron is also 1.6 into 10 raised to the power minus 19. It's just positive and negative, but the charges are the same, the elementary charge. So 4 pi epsilon naught is 8.85 power minus 12 from the data booklet. Then we get the distance between them, which is 1.5. Now please be advised, this is the radius of orbit. This is just this distance. We have to multiply this with 2 to find the distance between them. So this will be 2 times multiplied by 1.59. Right, 1.59 into 10 raised to the power minus 10 whole square. So this complete algebra comes out as 2.27 into 10 raised to the power minus 9 newtons. And we have to show that this is 2.28, so 2.76 it is. So this becomes 2.28 into 10 raised to the power minus 9 newtons. We have shown this successfully. Use the information in B2, which is this part. Determine the speed determine the period. Okay, so if you were unable to show this, that's why it's telling you to use this information to calculate this part. Okay, I've said that many times that if you're unable to show that in the previous part, you can use the value still in the next parts. That's why he gives those parts. Okay, so we have first we need to develop the logic as well, that the centripetal force in English, write this down in English. Centripetal force is being provided by the electric force, and we have calculated the electric force, which comes out as, or you can write this down like this. So electric force we found in previous part was 2.28 into 10 raised to the power minus 9 newtons equals to the centripetal force, which is going to be mr omega squared. You see, since he's asking me about the period, the problem is I have two formulas for centripetal force, mv square over r and mr omega square. Out of these two, only mr omega square is what gives me the liberty to use 2 pi by t whole square eventually. So the period time t can only be found by this. I could have used mv square over r, but I can't do that. And then I'll have to use the v equals to r omega. I'll have to use this at one more time or one more stage. So no point in doing that in two steps. We can do this in one single step by using mr omega square. So this is 2.28 into 10 raised to the power minus 9 equals the mass which is 9.11 into 10 raised to power minus 31, because we're working with an electron. And if you go to another booklet, you will find this value over there. So the radius of orbit is 1.59 into 10 raised to power minus 10 into omega square, right? Then omega comes out as a certain value, and if you 2 pi by t, if you find out the full answer, the value of t is going to come out as 1.58 into 10 raised to power minus 15. Okay. All right. So we've done that successfully as well. This will be 1.58 into 10 raised to power minus 15 seconds. That is how quickly they're rotating, by the way. So positronium is highly unstable. After a very short period of time, it becomes gamma radiation, of course, by the process of annihilation. He says what's going to happen to form these two, how gamma is formed. So the process is known as annihilation, and that is basically a collaboration of matter plus antimatter in quantum physics. So when when matter and antimatter collide, matter was the beta particle, beta negative, and antimatter was the positron, which was beta plus 1. The process annihilation takes place, right? And annihilation releases energy by the mass energy conservation, that this mass is converted according to the equation E equals to mc square into pure energy of the gamma photons, of the gamma ray photons. So I've explained the process to you. You can write this down in English. Okay. State 1 medical. Now we know that this is actually the PET scan, or the positron emission tomography, according to the new syllabus. Instead of MRI, this is PET scan. So what is the specific, again, a common definition from O levels? It is the energy required, energy needed, since this is specific, energy needed to change state. What type of change of state? From liquid to gas. Mention this, liquid to gas or to boil at a fixed temperature. For 1 kg, or per unit kg. Okay, that is specific. So this is joules per kg. All right, specific latent vaporization for water at atmospheric pressure is this. A mass is this. Liquid water at 100. It's already at 100, so it's just about to boil. It's at boiling point. Vaporize at atmospheric. Calculate the thermal energy supplied. So very simple. Q equals to ml. Mass is 0.37. And that is 2.3 into 10 raised to the power 6 joules per kg. So this comes out as 8.5 into 10 raised to the power 5 joules. So you've invested in this system, you've given it 8.5 into 10 raised to the power 5 joules to heat, not just to heat, but to change its state from liquid to gas. He says the mass of 1 mole of water is 18 grams. Vapor can be considered to be as ideal gas. Okay, show that the final volume is this. No problem, we will use the ideal gas equation because he says it's an ideal gas. So this will be PV equals to nRT. The pressure is atmospheric pressure, 1 power 5. Volume is 0.64. The current volume, of course, the moles will be calculated later. R is 8.31. And T is the final temperature, which is 100 degrees centigrade. So above 273. It has a temperature of 100 right now. The gas has a temperature of 100. Now, how to calculate moles? You see, he gives you 370 grams of water vapor, right? So this will be 370 grams mass over mR, which is 18 grams per mole. So this can be calculated over here. When you find the volume, volume was required. When you find the volume comes out as, because this is what we want to show, it comes exactly as 0.64 meter cube, which means that if you had this beaker, for example, if you're heating it up, if 0.37 kg water was present in it, now all of this has converted into a gas cloud which has a volume of 0.64 meter cube, which is a very huge number, by the way. Anyways, assume that the initial volume of the liquid water is negligible. Okay. The V1 is 0 and V2 is 0.64, final volume. Determine the magnitude of work done by the water in expanding against atmospheric pressure. So work done is equal to P delta V. Atmospheric pressure was constant, which was 10 into 10 to the power 5. The change in volume was 0.64 minus 0, because he says it's negligible, so that is 0. So that comes out as 6.4 power 4. So 6.4 into 10 to the power 4 joules. Now, since this is actually an expansion case, I have developed this shortcut from in the videos as well, that if this is expansion case, this will actually be a negative sign, because you have to take energy from the system to push against the atmospheric pressure and then expand successfully. So you need energy to do that. And where are you going to get that energy from? You're going to get that energy from the liquid itself, or from the reserves that are already present inside the liquid. Okay. So you either answer in B1 and B3. B1 was this, and B3 is this. So B1 is also in joules. B1 is also in joules, and B3 is also in joules. So we have the energy available for all of the system. He says, justify, what are we trying to find out? The increase in internal energy. Okay, so the internal energy is equal to Q plus W. Now what is Q? Q is simple heating. And what's W? P delta V. Now to find the internal energy change, simply put, because you provided the heat, the Q will be positive. So this will simply be 8.5 into 10 raised to power 5 plus, what happened with W? Did you compress it or did you expand it? So since it is expanding, why did it expand? Because you provided the thermal energy and allowed it to move freely. So that energy will be subtracted because it has been taken away from these reserves provided externally. So 6.4 into 10 raised to power 4. And of course, this comes as negative. In a common man term, this will still be subtracted because you gave this much thermal energy. Some of it has been responsible for causing the expansion or causing the expansion of the gas. So whatever is left will be a part of the system's internal energy. Simple. So this would be 7.9 into 10 raised to power 5 joules. Of course, this has been subtracted because that energy has been taken away due to expansion. Now, there is a simple way of understanding this part and there's a complicated way. He wants you to explain it in a complicated way, but let's try to first understand it in a simple way. You see, he says that using the first law, yes, we will do that. Specific latent heat of vaporization of water at a pressure greater than atmospheric pressure compares with the value of atmospheric pressure. You see, he's asking you that if ml was calculated at the atmospheric pressure level and ml was calculated at a pressure higher than atmospheric pressure, let's call this Q1, let's call this Q2. Which one will be greater? A simple common man prediction is that Q2 will be greater than Q1. Why is that so? You do this in IGCSE O levels as well. That for example, if you increase the pressure of a gas, for example, or of a liquid as well, then it becomes difficult for the liquid molecules to escape. It will be difficult for them to boil and escape and become a part of the atmosphere, right? Because you're increasing pressure. So gas has to do more work to push against this atmospheric pressure and then eventually become a gas. You see, they not only have to break the bonds, but they also have to push against the atmospheric pressure. So most definitely the answer of Q2 under high atmospheric pressure will be greater. You will have to make a larger effort to cause that liquid to boil. This is what we did in O levels, that when atmospheric pressure or pressure increases, the boiling point also increases because it requires more effort. Now this is a common man understanding. How to explain this in terms of A level? So using first law. So first law suggests that this is delta U equals to Q plus W, right? And we understand that delta U is equal to ml plus P delta V. Now let's take this P delta V on the other side. Let's take it over there. So this becomes delta U minus P delta V equals to ml. If you look at this equation, you will realize that in order for this to successfully take place, if you are doing this at a higher pressure, let's say that the pressure 2 is greater than pressure 1 initially. So this for the old case will remain as it is. But for the new case, when the pressure is high, this equation will change mathematically. So this is going to become P delta V equals to ml. But what's happening now? You see, since this is going to be a larger number, it will require more reserve. It will require more investment from the internal energy reserves. It will demand more energy to do the same job. If it is demanding to do the same job, in order to successfully complete the task, I will need to increase the heat energy so that this work can be completed and it cannot remove so much energy from the internal energy reserve already present in the system. Again, let's discuss this again. हमें ज़्यादा एनर्जी देनी पड़ेगी, हमें ज़्यादा एनर्जी देनी पड़ेगी, वही ओ लेवल्स वाली बात, ताकि ये वाला काम जिसका प्रेशर बढ़ चुका है, जिसकी पी की वैल्यू ज़्यादा है, डेल्टा वी आज भी वही है, वी आर स्टिल ट्राइंग टू डू द सेम जॉब, delta V is still the same, but since it has to be done at a greater pressure, you have to do more work to push against the atmospheric pressure. जब आपको ये काम ज़्यादा करना पड़ेगा, तो ये इंटरनल एनर्जी में से ज़्यादा एनर्जी इसको चाहिए होगी या इसको इस्तेमाल कर लेगा. अब अगर हमने फिर भी ये काम सक्सेसफुली करवाना ही है, तो हमें बाहर से हीट एनर्जी ज़्यादा देनी पड़ेगी ताकि ये काम भी हो जाए और ये इंटरनल एनर्जी से उतने रिजर्व ले जितना उसने पहले लिया था. It's all about investment. It's all about an accounting problem. How much investment do you need? How much energy do you need from internal energy, and how much energy do you need from the heat energy, or the at least this latent heat vaporization? So based on these two explanations, this is a simple one, and this is an A-levels complicated one. We will need, or the latent heat value at higher atmospheric pressure will be greater. So, हम justification कैसे देंगे? At higher pressure, at higher P, the work done is higher, right? Since delta U is equal to W plus Q, since W is higher, or this is a higher requirement, right? So Q will also be higher, which is proportional to ML. आपको latent heat ज़्यादा करनी पड़ेगी, heat ज़्यादा करनी पड़ेगी, because when it goes to that side, तो अगर आपका W नेगेटिव बढ़ता जा रहा है, बिकॉज आप उसको एक्सपैंड करने की परमिशन दे रहे हैं ना, तो आपको अपना Q भी बढ़ाना पड़ेगा. लेट्स से दिस बिकम्स फ्रॉम -200 पुराने केस में, ठीक है. इफ दिस वाज -200 तो आपको हीट देनी पड़ी 200 ताकि इंटरनल एनर्जी, चलो फॉर द सेक ऑफ एग्जांपल, 0 रहा, ठीक है. बट अब अगर आपने हाई प्रेशर पे ये काम करवाया एक्सपेंशन वाला, सो इट विल रिक्वायर मोर एनर्जी, सो नाउ आपको अपनी हीट भी बढ़ानी पड़ेगी ताकि ये काम कंप्लीट हो जाए, राइट. सो सिंपल मैथमेटिक्स प्रॉब्लम थी जिसको हमने फर्स्ट लॉ के थ्रू जस्टिफाई किया. दैट्स इट. ओके, ऑलराइट. सो स्टेट व्हाट इज मेंट बाय रेजोनेंस. अगेन अ कॉमन डेफिनेशन, प्लीज मेमोराइज दिस. This will be when the driving or external frequency, when the driving frequency or external frequency or the external factor becomes equal to the natural frequency of any oscillating object, the amplitude of oscillation becomes maximum, or you can say the energy addition becomes maximum. But you will graph it. This is that graph that we actually studied in the class, that this is the natural frequency. When you match it, you actually introduce the maximum amplitude in the system. That is how microwaves actually cook food. Okay, we match the resonance of water and oil molecules to heat them up, and then we provide that energy externally from the microwave so that they resonate at the water's and oil's molecule frequency, add its energy into the water or into the oscillation of the oil molecule, and eventually cause increasing energy, and that increased energy translates into higher temperature. Okay, so two pendulums are attached. Okay, fine. Same natural frequency. Okay, fine. Oscillating perpendicular. Okay, fine. So these are the two oscillating pendulums. Okay. All right. So they have the same frequency. He says this is the equation of the light pendulum. Okay. Calculate T of the oscillation. We can simply go back and read the graph for the light, but we don't have the values. Okay. So we have the equation. So we know the equation looks like x naught sine omega t. So whatever is written instead of t is actually a part of omega, right? So I can simply write this down as this. So my omega is equal to 2 pi by t, which is equal to 5 pi given in the question. So I need to find the t. So that will be t equals to 2 pi divided by 5 pi. So t comes out as 0.4 seconds. I believe so. Yes, 0.4. Since we need to represent two significant figures, so this will be 0.40. On figure 5.4.2, label both axes with correct values. Now we have to go back to 4.2 and label them. So if this, for example, x naught is 0.5, then this is 0.25, right? So then this would have been 0.5 and this would have been 1.0. Based on simple mathematics. This is 5 boxes. The next 5 boxes will be 0.25, 5 boxes 0.75, 5 boxes up to 1.0. So we have to label it in this way. Plus the labeling of this one will be in negative 0.5. This will be in negative 1.0. Simple. The displacement has been done. Now let's figure out the value for time period. So simply put, this one complete wave will require 0.4. This will be 0.2. This will be 0.6. This will be 0.8. This will be 1.0. This will be 1.2. Simple. Okay. All right. Determine the magnitude of the phase difference between the oscillation waves. Now, very simple question. This is from AS level question. Very, very easy. You could have visualized it from 2 to 3 different places. Let me do it for you. So let's zoom in and see where we could have picked the values. So let's say that this is that situation. Okay. You could have picked the gap between the peaks, which was very simply located over here. So you could have selected, for example, the peak of this graph located at this point. Let me increase the thickness of the marker. Okay. So you could have picked this value from the graph, and you could have picked this value from the graph. The difference between the times would be what is required for the phase difference. You could have done this, or you could have taken this gap when both become 0, either from this side or either from this side. Does not matter. Okay. What we're interested in is when they get the same value. How far away are they when they get the same value? Let's look at the crest side of the waves. Can we do that from this side? Sorry, trough side. So it could have been from this location. Very easy. So pick either this location, okay, and this location, right? So the gap between them. So no matter where you look at them, because we're looking at the maximum negative displacement, when do they get the same values? This is the logic behind it. And whenever they do get that, we will check the delta T. What's the difference between them? So this will simply be delta T divided by T multiplied by 360, or you can do this with 2 pi to get the answer in radians, right? So delta T comes out as 0.1, and the T time period for one oscillation is 0.4. Now, is it different for both of them? No, it's not, because he mentioned that they have the same natural frequency. They are oscillating at the same time period. They have the same time period. If you look at the light one, either if you look at the heavy one, this T will be 0.4 for both graphs. You can check this on your own as well. So simply multiply this with 360 or multiply this with 2 pi. You will get your answer. If you do this with 360, your answer becomes 90 degrees. If you do this with pi radians, this comes out as 1.6 radians. Of course, after multiplying the value of pi, which is 3.142. So you can either write down 90 degrees or you can write down 1.6. So 1.6 radians, which is RAD rad. Question number 5 of capacitance. In parallel plate capacitor, define the capacitance. Now, the capacitance has the formula Q equals to CV. This is what we want to define. So C equals to Q divided by V. Now just explain this ratio in terms of English. You will say that it is a ratio of charge held on the plates to the potential difference across the plates. So you will say ratio to depict the division of Q, charge held on the plates, to the divided by potential difference across the plates. Simple. Okay. Now we have two capacitors connected in this format, C1, C2, parallel. Okay, voltage will be same. He says prove that this is the case. Okay, and explain your reasoning. You see, since they are in parallel, the voltage is same. Voltage is same, or you can say that the voltage of capacitor is equal to the voltage of the battery for both of them. This is the first reason. Okay. Second thing would be that the charges dispersed in the battery or charges dispersed by the battery will be added together. If added together, will be equal to the charges dispersed by the battery. So if the battery has sent, let's say, 10,000 electrons, this one saved 6,000, this one saved 4,000. Add them together, this will become equal to 10,000 electrons that the battery has actually sent. So I understand that the charge addition will be the same. So total charge of battery is equal to QA, or charge by first capacitor plus charge by second capacitor. So we're going to start from this idea. So the total charge is equal to charge of 1 plus charge of 2. And we know that Q equals to CV. Let's replace that in this equation. So this becomes CV equals to C1 V1 plus C2 V2. And since we know the voltage is same because it's connected in parallel, right? So this V1 and V2 cancels out by taking them common on the outside. Mathematically speaking, that's what's happening. So CV equals to V into C1 plus C2. This is what happened. So V cancel out with V because they're in parallel, voltage is same. So the total capacitance comes out as C1 and C2 added together. Then in place of these two, I could have connected just a single capacitor that had a value of C1 plus C2 as an equivalent capacitance. So now he is going to move towards the mathematical aspect of this chapter. He says, okay, the circuit is given to us. Okay, fine. First, he will charge the capacitors with the help of the batteries, right? And then he will connect or move the switch towards the resistor to remove that energy into the resistor or discharge that capacitor into the resistor. So he says that the battery has an EMF of 12 volts. Okay, fine. Show that the combined capacitance is 15. So since they're connected in series, please be identified. So the formula we will use is going to be 1 over C plus 1 over C equals to 1 over C. So this would have been a 1 over 22 plus 1 over 47 equals to 1 over C. The common mistake that you do over here is this, that when you're done with this on the calculator, you don't take the reciprocal. You see, you're finding C. You have to take the inverse on both sides. So the capacitance comes out as 15 microcoulombs. Now you might be worried that I have not included the microfarad. Okay, so it doesn't matter. Since micro is with the whole system, the whole equation, the microfarad will be carried until the end in terms of mathematics. So no need to worry about that. So two-way switch X is at X and now fully charged. Use information at total energy. So now the total energy is simply half CV square. Half. The combined capacitance is 15 microfarad. This is what they could do collectively. So 15 into 10 raised to the power minus 6. Into voltage is 12 square. He says that the fully charged voltage is 12. Okay, fine. So this comes out as 1.08. This is 1.08 into 10 raised to the power minus 3. So this will become 1.1 into 10 raised to the power minus 3. Two significant figures. The two-way switch is now moved to position Y. As expected, he's moved that position to position Y. So it does not exist at this point. It exists at this point. So it's not here anymore. It's not here anymore. It's actually at this location. It's connected like this. So now the only circuit that we can see is actually this one. Let me erase the rest of them so that it becomes easy for us to visualize. This is the rest of the circuit that we can see now, right? So it's just a resistor connected with two capacitors in parallel or in series, right? But no, this is in parallel, by the way, right? Because the voltage or the representative, actually this one, had 12 volts across them, was 15 microfarad, and now the same voltage would show up across this resistor. So this whole setup is actually in parallel to one another, at least when you're going to visualize them as a single unit. Okay, so let's move on. He says find the time when it actually comes down to 6 volts. The potential of 22 microfarad comes down to 6 volts. Now, since they are in series, their voltage will be divided and they will be sharing that voltage. But how much voltage is going to be captured by the 22 microfarad if this was the case? So let's try to do that. You see, what we have over here is a circuit that looks like this. So we have this as 22 microfarad. This is 47 microfarad. And we don't know their voltages, individual voltages, but we do know about their capacitances. And we do know that the total charge they held can also be found. You see, we can use this equation Q equals to CV. Since they are in series, the charge held by both of them will be the same. So Q equals to CV to find the total charge. That would have been Q equals to capacitance, which is 15 microfarad minus 6. And voltage is 12. This total charge comes out as 15 E minus 6 into 12. The total charge they held was 180 microcoulombs. Now both of them have equal charges because they are in series. And what's the logic behind it? You see, the number of electrons gathered on this plate have repelled the same number of electrons to gather on this plate. So the number of charges or the number of electrons on both these plates is exactly the same. So this is one way of looking at it. I'm going to explore 2 to 3 methods to simplify this. Now we can use this information to find out the voltage across this capacitor. So again, using Q equals to CV, I realize that the charge is same. So this will be 180 into 10 raised to the power minus 6 equals to the capacitance. Its own capacitance is 22 micro. So minus 6 into the voltage of this capacitor. So this voltage comes out as, so 180 minus 6 divided by 22 minus 6. This comes out as 8.2 volts, right? This is 8.2. This is one way of doing this. Another way of doing this would be to compare the voltages. We know that this is being compared, or this has a total voltage of 12 volts. So we can compare this with using Q equals to CV. We know that charge is same. So voltage is inversely proportional to the capacitance. This is the equation that we can use. So how to use this? So we can compare this with another situation of voltage with another capacitance. Okay, fine, no problem. So according to this system, if let's say, I'm doing this again over here. According to this system, 12 volts are required to maintain a system of 1 over 15 microcoulombs. This whole divided with X voltage, I don't know what that voltage is. What would be the voltage if out of this it had a capacitance of 22 or 1 over 22? When you're done with this algebra, you will again get the voltage of 8.18, which is exactly the same, based on the same premise. The charge is same. So I've done this ratio step by step over here to find the voltage and then the charge. It's your choice how you want to visualize this. It's okay. It's fine. Okay. All right. Whatever method you think is easy for you, you can do that. So we have found the initial voltage carried by this capacitor. So the equation goes something like this. V equals to V naught e raised to power minus t by RC. Now we have the current voltage of today, which is 6. We have the initial voltage previously, 8.2. We do have the time. This is what we want to find out. Time is the required quantity, but we don't have the RC. RC is tau, the time constant. So tau can be found by simply RC. So what is the resistance of the circuit experience? So that is 2.7 mega. So that is 2.7 into 10 raised to power 6 multiplied by, what is the capacitance of the complete circuit? The capacitance of the complete circuit was actually 15 into 10 raised to power minus 6. Okay. So this tau is equal to 40.5 seconds. So we're going to put this in place of RC. So this equation is going to look like this. 6 equals to 8.2 e raised to power minus t divided by 40.5. Don't round this off to 45. The answers will be different. So keep this at 40.5. First solve this. Okay. Now again, a simple mathematics trick over here. I've explained this in other videos as well, that if you take this over there, this becomes 6 divided by 8.2 equals to, now if you take the anti-log, this will become ln of 6 over 8.2 and negative t divided by 40.5. Now we have known this by mathematics, that if you divide, or if you take the ln of a small number with a large number, or in this division, the answer becomes negative, but the answer will come out as negative. So this negative cancels out with this negative. So the overall answer of t will become positive. So this comes out as 12.65 seconds. So roughly it will be around 30 seconds when the voltage drops from 8.2 to 6. So the graph will look something like this. It starts from 8.2 and goes down to 6 in a time frame of 13 seconds. Right? The discharging graph of the capacitor that we've learned in the class as well. Okay, so I've gone in great detail for this question. Okay, question number 6. State 2 condition, satisfy the copper wire to place magnetic field, experience magnetic force. So there needs to be a current in the wire so that it can have its own magnetic field, and that magnetic field should be perpendicular to the magnetic field of the external magnetic field. So how can we do that? So that the current and the magnetic field should be perpendicular to each other. This is what we experience in Fleming's left-hand rule, by the way. So this is north, this is south, and if this is the conductor, for example, carrying current in this direction, the magnetic field is in this direction, they have an angle of 90 degrees. Only when they have an angle between them, the force will be experienced. Being perpendicular is not necessary, but the angle should be at least greater than 0. It can't be possible that the magnetic field is in this side and the current is also in this direction. It will not exert, or it will not experience any force. That will be incorrect. Okay, so the magnetic field is given to you about the W, the dipole's direction. That means that the north is over here, the south is over here. If you were to figure out the direction of the current in the coil, which is not required, but we could have done that, you will use right-hand grip rule. How would you do that? You will place your thumb in the left direction, according to this direction of the north pole, and then you use the right hand, by the way, right? So you will curl your fingers above this coil to grip it like this, using your right hand. So this is what your right hand will look like. Okay. So the thumb points to the direction of north, your finger points to the direction of current. So this will be a current that is into the page as represented by cross, and this will be the current. Downward side will be the current represented by dots as out of the page. As your finger grabs it goes into the page, and grabs it outwards, it comes out of the page. So just another question, just another idea for another topic for another day. If the question might have been asked in this regard, it's going to ask you to make the arrows of magnetic field at each x, y, and z. So x will still be in the same direction, approximately same strength, same direction, same orientation. Now, since we know that for a bar magnet, the magnetic field goes like this, and you know solenoid also behave like this. So it will be somewhere along this line because it has to complete the curve over there. Okay, it can't be straight, it can't be this direction, both are impossible. So this would have been this. And over here, the direction will be in this direction, because to complete this loop, this is what it should look like. And this is basically an O-levels question or IGCSE question. Very simple, very straightforward. He says compare the magnitude and the flux density. Okay, at X and W. X and W, they will exactly be the same, or roughly be the same. And Y and Z. Y and Z. Here it will be stronger because it's closer to the magnet. Here it will be weaker as it's away from the magnet, and there are more number of magnetic field lines being drawn over here as opposed to this place. Okay, all right. Again, this question is from O-levels IGCSE. He says explain by two parallel long wires how the magnetic force actually comes into place. So you can simply explain the question by drawing two magnetic fields or drawing two conductors carrying current and showing their magnetic field like this, that they are carrying current in a single direction, for example, or an opposite direction, does not matter. And they have a magnetic field around them, which is going to be circular in nature, like this. Now, this is, of course, the 3D visualization. If you were to draw this in terms of 2D, this, based on where you're experiencing, where you're viewing it from, if you're viewing it from the top, then this would have been a current out of the page, and this would have been current into the page, right? This current is moving away from you, this current is moving towards you. So when you justify it in that regard, you could have used the right-hand grip rule to figure out the direction of magnetic field, that this will be in this direction, and this will be in this direction. So at the center, the magnetic field is in the same direction for both of them, even for this one. The magnetic field is in the same direction. On the outer side, the magnetic field is in the opposite direction. So the force is always exerted from an area of strong magnetic field towards an area of weak magnetic field. From strong to weak, they will repel each other. This is what you can write down over here. You can simply say that the magnetic field is due to the current around the conductor. It is circular. Explain its nature, right? And the wires experience each other's magnetic field. Or you can say that this magnetic field is experienced by this one, and this magnetic field is experienced by this one. So both are experiencing magnetic field of each other. And as we can see that the current is perpendicular to the magnetic field, there will be a force due to Fleming's left-hand rule. Simple, right? Okay. Question number 7, Faraday's law. We have done this before as well, that the rate or the induced EMF is actually proportional to the rate of change of magnetic flux. Okay. So you can see this information from the book or from the marking scheme as well. This is a repeated question. Exactly same question was in October, November 2022 as well. 100% same, exactly the same coil, same question. This time it's a bit difficult. So we are supplying this voltage ourselves, and this is what we are detecting. This is what we are measuring. It says that the variation of magnetic flux in coil 1 is given. Coil 1 is given. And we know from experience that the magnetic field is proportional to the current. If you increase the current through any wire, its magnetic field becomes stronger. We know that. So either we look at it from the perspective of B or I, it's the same. And I'm guessing, yes, the next question is about voltage. So to understand induced EMF, we need to understand that this is rate of change of magnetic flux, which is equal to BA divided by T. So in turn, we are checking the change in B, or the change in magnetic flux, divided by the time taken in which it was done. So let's try to draw this graph. It's a very, very expensive graph in terms of marks at least. So we'll have to be very accurate about this, and there should be some points that are difficult to figure out. Let's see. So first transition we see is going to take place at 1.5, the second transition at 2.5 or 0.25. So first I draw these two coordinates, at least, that this is where I'm going to see the transition. We've established that according to Faraday's law and Lenz's law, there needs to be a negative sign in this. So if the gradient is positive, then the EMF will be negative. Similarly, the gradient is negative, the EMF will be positive. the gradient is positive, the EMF will be negative. So based on this idea, I can see that over here I will cover the negative region, over here I will cover the positive region, and over here I will cover the negative region. So the pulse is going to go something like this: negative, then positive, then negative again, according to the Lenz's law. This is my prediction before starting the question. Now let's figure out what will be the exact magnitude of voltage. We have to let some values and see what we can get. Let's zoom in. So first, in a time frame of 0.15 or 1.5, let's make it 1.5. So 1.5 can be represented as 3 by 2t, right? So 1.5, this would have become initial change of this section would have become EMF, a change of B was experienced in 2 by 3t. So this will be the induced EMF in the first section. Okay. All right. What about the second section? I'll draw this later. What about the second section? See, in this section, we have to be careful that two things are happening. First, we increase the change from not only to go from B to 0, but it has to go to negative B as well. So in the second stage, we realize that for the change of EMF, the change in B is from B to 0, then 0 to negative B. So the change becomes 2B, twice the change. But what about the time? What has happened to time? You see that this is 0.15 and this is 0.25. So the change happened only in 1 time second. Now we have to compare the EMF original or the EMF of the first section to the EMF of the second section. So what does that look like? So EMF of the second section divided by EMF of the first section, just to develop a ratio. So EMF of the second section is this 2B. So 2B by T divided by the EMF of the previous section, which is 2B by 2. So this is 2B divided by 3T. Now we can very quickly realize that this B by T and B by T gets cancelled out. This 2 cancels out with this one and we get 3 times. That means that EMF of the second region should be 3 times the EMF of the first region. There should be a 3 times gap, 3 times ratio between them. This is required to draw the graph. Okay, so let's go back. If I am assuming that I need to draw 3 times the graph, then I'll have to count the boxes carefully. Please do that carefully, otherwise you will get it wrong, right? So let's make the graph. Let's say that this is 2E and this is 4E. So labeling the axis would be important. Negative 2E and then negative 4E. So in the first section, I will get 1E, standard value. And as predicted, I will draw negative EMF because the gradient is positive. I have to draw opposite in terms of Lenz's law. And then 3E, which is going to be somewhere in the middle. So then go to 3E, maintains 3E because it's constantly changing EMF. Then come down again because the gradient is positive again. So the EMF will be negative again. And exactly the same as before. Let's redraw this again. So this will be somewhere along this line and goes back to this. This is how it's going to be. Okay, and then you can confirm the marking scheme. This is the shape that's going to look like. And of course, if a student draws the opposite, if a student draws it like this, they will give you the credit. But if someday this Lenz's law is also included in the question, then what will you do? So that's why I'm explaining it in terms of Lenz's law as well at the same time. Okay. Coil is given to, this is a very common interview question as well. I've experienced this question in engineering interviews as well. He says that a coil is placed, copper ring is there, magnetic field coil is there. Okay, fine. He says, explain what happens when you close the switch. Copper ring is observed to jump. He says, why does that happen? You see, there is no current in the coil, no current, no magnetic field. When they close the switch, the current increases from a 0 value to a high value. So this is, let's say, a current. Now, when the current increases, for this region, we can say that the magnetic field is also changing because current is the cause of magnetic field, at least in a piece of wire. If high current is there, magnetic field will be higher. Now, this changing magnetic field because it is changing. After this, there will be no change. So it rose from 0 to a certain value. So there is a change in magnetic field. Although this happened very suddenly, because at the moment you close the switch, this has already happened before you can even notice it. So when there is a change of magnetic field, we can see that there will be an induced EMF according to Faraday's law, because that is proportional to the rate of change of magnetic flux. We know that, right? So when there is an induced EMF, let's say there is an induced EMF. Now that induced EMF causes the flow of current in the iron ring, and that current will of course produce a circular magnetic field around the ring in this fashion. That magnetic field interacts with the magnetic field of this coil according to right hand grip rule, for example, that this is the north pole, this is the south pole. Of course we can do that for the sake of example. And these two magnetic fields are interacting with each other, and we can observe that they will repel each other, and as a result the copper ring will go upwards. So we just have to explain this whole method over here, that when the switch is closed, right, there is a change in magnetic field. This causes induced EMF. That causes induced current. In which part? In the ring. That causes induced EMF in the ring. Now when there is induced EMF in the ring, that causes induced current in the ring, and that induced current creates its own magnetic field. So now ring current has a magnetic field around it, right? Now when it has a magnetic field around it, we move forward. That magnetic field interacts with the coil's magnetic field that we found by Fleming's right hand, it's not Fleming's, but right hand grip rule, and as a result there is a repulsion and it jumps. Okay, all right. So just with reason, would be any effect repeating the procedure where the terminals are set reverse? No, there will be no difference in the output. Why? Because if you change the terminal, the current is going to go from this side, probably north and south will be formed in this way, but there will still be a change in current. And this is what I actually told you about, where the Lenz's law actually comes into place. You see, now, since the current is moving in the other direction, right, we can say that the magnetic flux has changed from 0 to a negative direction. Now, when that happens, the induced EMF will actually be positive. Now, when that induced EMF actually goes into the coil, it creates a current in the opposite direction as opposed to before. The coil will still jump. You see, this is why I'm telling you that Lenz's law is important. So the answer will be that the coil still jumps. Reversing the direction of current also reverses the direction of induced EMF on the coil. Why did this happen? Lenz's law. Lenz's law tells you about the opposition. That whatever you do, I will do it opposite. So state one piece of experimental evidence, particle nature of electromagnetic radiation. So what is the particulate nature? What tells us, what gives us the license or the guarantee that electromagnetic radiation is a particle? So the photoelectric effect. And we use photoelectric effect in solar panels to produce electricity. Wave nature, electron diffraction. Now why electron diffraction was important? That's an important question. How did we know that wave is actually compared to matter? You see, matter goes through diffraction. Waves go through diffraction. Couldn't we do it with something else? We could have done that, but the problem is that even if you use an alpha particle and pass it through a narrow gap, or at least through a filter, or at least through a diffraction crystal, it will be absorbed. It's very difficult for alpha particle to pass through it. And any particle larger than that would be another impossible scenario. It can't be done. So we need a particle that is much smaller than alpha particle, has some mass, and can pass through very narrow gap at high speeds without interacting with any other particle, right? So the obvious choice was electron. So if electrons are diffracting, that means matter as we know it, for example, a kilogram of copper, a kilogram of sand, a kilogram of, let's say, anything, any substance in the universe will go through diffraction if passed through a narrow gap at a high speed, of course. Calculate the de Broglie's wavelength of alpha particle moving at this speed. So the wavelength formula for de Broglie is very simple. We mentioned in the syllabus as well. So lambda equals to h divided by p. This is what we want to calculate. So lambda equals to, the Planck's constant is 6.63, 10 to the minus 34 divided by momentum. The mass of alpha particle is 4 times into the standard mass unit, minus 27. Now P is momentum, by the way, right? So this is the velocity, which is 6.2 into 10 raised to power 7, positive 7. So lambda of alpha particle comes out as 1.61 into 10 raised to power minus 15 meters. What does this mean? What is the significance of de Broglie? Why is he remembered like this? What did he contribute? He said, this equation is very nice. This is actually h by lambda. Sorry, h by p. Lambda is a characteristic of a wave. Momentum is a characteristic of a particle. So he in turn connected the wave nature and the particle nature of matter as it moves through space. What he said was that when you observe it, it can be looked at upon as a particle. And when it moves through space, every matter has a wavelength when it is moving, even if you are moving, for example. Let's say you have a mass of 80 kg and you're just walking by at a speed of 5 meters per second. You can use lambda equals to h by p, calculate your momentum, divide this with Planck's constant, and you will find your wave function as well, how you move through space, right? A very, very interesting topic, very interesting point by de Broglie. He connected wave nature with particle nature, okay? So that's why he's important. That's why he's remembered. So this is 1.61 into 10 raised to power minus 15. This is in terms of V and lambda. So very simple. We have the de Broglie's equation as lambda equals to h by p, which becomes lambda equals to h by mv. So we can compare this lambda being inversely proportional to velocity. This is on y-axis and this is on x-axis. So we can see that there's an inverse relation between them. So this would have been something like this. Simply as y being inversely proportional to x. This is that graph. Simple. Okay, so just an explanation why people are not exactly. ये वही सवाल दोबारा आ गया जो कि मैंने भी आपको बताया था कि ह्यूमन बीइंग्स भी डायफ्रैक्ट कर सकते थे अगर हमारे पास इतनी छोटी वेवलेंथ, इतना छोटा गैप आ जाता था. सो व्हेन वी आर मूविंग थ्रू स्पेस, वी आर मूविंग लाइक अ वेवलेंथ, वी आर मूविंग लाइक अ वेव. सो इसका आंसर क्या बनेगा कि जो हम ह्यूमन बीइंग्स की de Broglie's wavelength है, de Broglie wavelength is much smaller and we don't have a gap that is small or at least this much, or is it comparable with this? अगर हमारे पास ये गैप होता किसी दरवाजे में, लेट्स से किसी विंडो में, तो ऑफ कोर्स हम उसमें से गुजरते तो डायफ्रैक्ट करते. एटलीस्ट थ्योरी तो यही सजेस्ट करती है. द थ्योरी सजेस्ट दैट दिस कुड हैव हैपेंड बट वी डोंट नो वेदर इट विल हैपन और नॉट. सो अगेन de Broglie's equation is very important. It connects wave with particle. Question number 9, Hubble's law. He says state Hubble's law. So again, V proportional to D. You can say that the speed of recession or the speed of moving away of any galaxy is proportional to the distance from the observer. वो जितनी ज़्यादा दूर होगी उतनी ज़्यादा स्पीड से हमारे से दूर जा रही होगी. ठीक है. Galaxy away from the observer. Okay. Explain how cosmologists use observations, emission spectra from stars and distance to galaxy to determine the universe is expanding. Again, Big Bang Theory की explanation है. और ये सवाल मई जून आपके पास अक्टूबर नवंबर 2022 में भी आया हुआ है कि होता कैसे. तो बेसिक थ्योरी है, वेरी सिंपल आंसर, दैट लैम्डा इन लैब इज कंपेयर्ड विद लैम्डा ऑब्जर्व्ड फ्रॉम द यूनिवर्स. एक लैम्डा आपने लैब में ऑब्जर्व किया और हाइड्रोजन गैस के ही कर लेते हैं. ठीक है. आपने लैब में देखा कि उसकी ये वेवलेंथ आनी चाहिए, उसका एमिशन स्पेक्ट्रम ऐसा होना चाहिए. ठीक है. लेकिन जब आपने एक्सटर्नल किसी स्टार का मेजर किया फ्रॉम द आउटसाइड गैलेक्सी, एंड स्टार ऑफ कोर्स आर कंज्यूमिंग हाइड्रोजन and making helium, for example. So unka spectrum was slightly displaced. Their wavelengths were slightly off than what we observed. And we know that they're made out of hydrogen. They should have given us the same answer, but they're not. So their wavelengths are slightly displaced and they're slightly closer to the lambda of 700, which is the red color. That is why we call this the red shift. Okay. So observed are greater than the actual measured in the laboratory. So this concept is known as the red shift, and it came from the Doppler effect, that while the objects are moving away from us, their frequency will decrease. If their frequency decreases, their lambda increases, which is why हमें ज़्यादा बड़ी wavelength नजर आना शुरू हो जाती है as opposed to what it should have been. So this red shift, फिर Doppler effect का जिक्र करें, ठीक है, and red shift actually shows, or Doppler effect shows, that if the wavelength is increasing, the frequency is decreasing, and the source of that radiation is actually moving away from us. Hence, the universe is expanding. एंड इफ द यूनिवर्स इज एक्सपैंडिंग, तो इसका मतलब है कभी ना कभी एक्सप्लोजन हुआ होगा, और अगर एक्सप्लोजन हुआ और आज वो हम सब एक दूसरे से दूर जा रहे हैं, तो एक टाइम होगा जब सारे एक जगह पे इकट्ठे थे. एंड दैट इज व्हाट वी डिफाइन एज द बिग बैंग थ्योरी एंड व्हेन द यूनिवर्स मस्ट हैव ओरिजिनेटेड. सो वो यही आपसे आगे पूछेगा, हाउ हबल्स लॉ हेल्प द प्रेडिक्शन ऑफ यूनिवर्स लेड टू द एक्सप्लेनेशन ऑफ बिग बैंग थ्योरी और द ओरिजिन ऑफ द यूनिवर्स. सो universe is moving away from each other. So there must have been a time in the past. In the past, of course, there have been a time where they were together, when they were collected at a single point. Okay? And must have been close together, and it would have been dense, right? So, and today they're moving away, and they're moving faster and faster, according to Hubble's law, which is this. So you can use these ideas to explain this answer. Then you can consult the marking scheme to memorize the points at least. But this is very well explained in the book as well. What is meant by reactive decay? Again, a repeated question. You can see that at least in 10 questions, there have been 2 marks of definitions in every question. So 10 multiplied by 2, 20 marks are purely of definitions. So out of 100, you get 20 for just definitions. And to get an A star, you have to cross the boundary of 80. So out of, let's say, if you want to make an A, you have to cross 65 out of 100. If you want to get an A star, you have to cross 80 to 85 out of 100. Now, if you don't take these definitions lightly, according to their due importance, if you don't give them their due importance, what are you losing? You can't attempt the whole paper with 100% accuracy. So you're already losing 20 marks. You're already losing that margin that you would have gotten for at least getting an A star. So get these 20 marks, and then you have to score only 65 out of the rest of the paper. If you get full marks in definitions, you will get to A star. So please pay attention to these definitions. Go through 5 to 10 or 5 to 7 examination papers and mark every first question or every definition and make your own notes from those definitions. I'm sure that you can get at least 30 to 35 definitions from 5 to 7 years of paper, and then you're done. You have a data booklet or you have a bank of definitions which you will memorize before going for the examination. So reactive decay, it is a spontaneous emission. Spontaneous, why? We didn't do this. It's happening on its own. Spontaneous emission of radiation from a radioactive nucleus. Okay, alpha, beta, and gamma, of course. Radio sample consists of this activity is this, contains this much number of atoms. Sketch the graph present at up to 3T. Does he mention about the half-life? Yes, the half-life is mentioned as T. So up to T, we have to half every number. So we've done this in O-levels as well. That you start with N naught, the next fraction is N naught by 2. The third fraction is N naught by 4. The next one is N naught by 8. So you keep on reducing it half, or you keep on halving the value. Okay, so the first time it is going to go from 0. The second time it goes N by 2. This is actually N by 2. At 2T, this would have been N by 4. This would have been at this point. And at 3T, this would come down to even N by 8. Now please calculate this 1 by 8. This will be 0.125, I guess. And then count the number of boxes exactly and precisely. Right? This will be checked. And this comes out approximately 5 boxes away over here. And then we can draw a freehand diagram with the lead pencil. And this will go down like this. The decay curve that you've done in O-levels as well, that looks like this, based on this half-life graph. Okay? All right. Now he asks you to find out the activity graph, or the graph of the activity. So what's that? So he says that sketch the graph of N activity A, sample values of N between N0 to N0. We had the formula as A equals to lambda N, and we can see that A is proportional to N, right? And N is the number of undecayed atoms. So between activity and N, there is a direct proportionality. So it's going to look something like this straight away. So at 1A, we will see 1N. So we have this coordinate over here, which is going to look something like this. Okay, a straight line, right? And of course, the gradient of this will represent the decay constant. Why? Because y divided by x. On y-axis we have A, on x-axis we have N. So A divided by N according to this formula is to take N over there. This becomes A over N. That becomes the decay constant, which of course he asks you that this is actually the decay constant. Then figure 10, sorry, gradient 10.1. So this is it, 10.1. 10.1 is the previous graph, which is this one. So what does this tell you? You see, we understand that from this equation, we have activity equals to rate of decay, which is delta N by T. So this delta N by T is represented over here. Y-axis divided by x-axis, which was time. This was actually activity. So the gradient of this graph represents activity, and 10.2 shows the decay constant. Now he says that find out these values at this location. So for sample in B, fraction n by n naught when time t equals to 1.70. Now t, please advise, is the half-life. It is the half-life. Okay. Okay, no problem. So we want to calculate the fraction. So that would be approximately up to this point, 1.7, let's say. Okay. This is just a prediction. Don't do this. We have to do this mathematically. Graphically speaking, I think he would not give you, he says calculate, so I don't think that he's going to expect you to pick this up from the graph. So we have an equation that is n equals to n naught e raised to the minus lambda t. We know this equation. We want to calculate the ratio of n by n naught equals to e raised to the negative lambda t. Now decay constant has another equation from half-life. That was that lambda is equal to ln of 2 divided by the half-life. Now in our question, capital T represents the half-life. So this lambda is equal to ln 2 divided by capital T. So I can replace this in the equation that I've written down over here. So this comes down as, now I'm dealing with the power of E, so I'm going to write this down in large letters. So negative lambda came out as ln 2 by 2. So ln 2 divided by T, this is lambda, multiplied by T, which was given to me in the question as 1.70 T. This is where we want to find the ratio, right? So T cancels out with T, and ln 2 is being multiplied with 1.7. This is a negative power on the outside. Be careful when you calculate this. You will get the answer of n by n naught as equal to 0.3077, which is going to be 0.31 up to two significant figures.